You know, science isn't just about those big, flashy eureka moments. A lot of the time, it's about the invisible rules humming away in the background, the ones that make all those discoveries even possible. So today, we're going to pull back the curtain on the fundamental grammar of science, how we measure, describe, and ultimately make sense of our universe.
But first, to kick things off, let's start with a little pop quiz. Take a look at this equation right here. 12.9 grams minus 7.06 grams equals 5.8 grams. Now, if you punch that into your calculator, you're going to get 5.84. So, is this equation correct? Just take a second. What's your gut feel?
If you thought, no way, that looks wrong, you are not alone. I mean, by the rules of your high school math class, it is wrong. But, and this is the key, by the rules of scientific measurement, it's absolutely 100% correct. And figuring out why is going to open up a whole world of crucial ideas about how science actually works.
To really get this, let's do a little thought experiment. Let's imagine a world without any rules for measurement. Picture trying to follow a recipe where your cup is a coffee mug, but your friend's cup is a tiny teacup. Or trying to build a house where your foot is literally the length of your foot. It would be total, absolute chaos, right?
Well, believe it or not, for a huge chunk of history, this was pretty much the reality for science. You had scientists in different countries, sometimes even in neighboring labs, all using their own local systems. This, as you can imagine, led to just massive confusion, tons of errors when people tried to replicate experiments, and it was a serious roadblock to making any real progress.
I mean, just take a look at this. This gives you a little taste of the chaos. You had the CGS system, which used centimeters and grams. Over in another part of the world, they might be using the FPS system with feet and pounds. And then there was the MKS system with meters and kilograms. Trying to translate results between all of these, it was a complete and utter nightmare.
Obviously, this just couldn't last. If science was going to become a truly global effort, it needed a universal language. And thankfully, that's exactly what it got.
And that's where the Système International d'Unités comes in, or as we all know it, the SI system. It was created to be a single, logical, and universal set of units for pretty much everything. It's the reason a physicist in Tokyo can pick up a paper from a biologist in Toronto and immediately understand what their measurements mean. No crazy conversion charts needed.
Now, the real genius of the SI system is how it's built. It all starts with just 7 fundamental building blocks. These are called base units. You can think of them like the primary colors of measurement. From these 7, you can mix and create every other unit imaginable.
And here they are, the magnificent 7. The meter for length, the kilogram for mass, the second for time, and so on down the list. Just about every other physical unit you've ever heard of, a joule for energy, a watt for power, a newton for force, it's all just a combination of these 7 fundamental ideas. It's like the alphabet for describing the physical world.
Okay, so problem solved, right? We have a standard unit, like the meter. Well, not quite. Having a standard unit actually creates a new, more subtle problem. For instance, if I measure a table and say it's 1.5 meters long, and you measure it and say it's 1.500 meters long, did we just say the same thing? In the world of science, the answer is a big no. And that difference is all about precision.
This is where we get into this really important idea of significant figures. See, in science, the numbers you write down are more than just a value. They're a statement about how confident you are in that value. Significant figures include all the digits you know for sure, plus one final digit that you've had to estimate a little. It's like saying the time is 10:31 versus saying it's about 10:30. One is way more precise, and significant figures are how scientists communicate that difference on paper.
Okay, so how do you actually spot these sig figs? Well, the rules are pretty simple. First up, any number that isn't a 0, it's always significant. Easy enough. The zeros are the tricky part. Zeros at the very beginning of a number, like the ones in 0.004700, are just placeholders, so they don't count. But, and this is crucial, zeros at the end of a number that has a decimal point, oh yeah, those are super significant. They're telling you how precise your measurement was. So for our example here, we have 4 significant figures, the 4, the 7, and those 2 important zeros at the end.
All right, armed with this new knowledge, let's go back to that mystery equation from the beginning. We're subtracting 7.06 grams from 12.9 grams. We've got the numbers, but now we know we also have to respect their precision. Okay, so here's the secret rule for adding or subtracting in science. Your final answer can't be more precise than your least precise measurement. It's all about honesty. So let's look at our numbers.
12.9 has 1 decimal place. 7.06 has 2. The least precise number is the one with fewer decimal places, so our answer has to be rounded to just 1 decimal place. The calculator says 5.84, but since we can only keep 1 decimal place, we round it to 5.8. And mystery solved. The answer is 5.8 because that's the most honest answer we can give based on our original measurements.
So we've got our universal language, and we know how to be honest about precision. But there's one more hidden rule we need to talk about. And this one is powerful. It's like a physicist's built-in baloney detector, a quick way to check if an equation is even possible in the real world. Let me ask you a question that sounds completely ridiculous. Can you add your car's speed to the weight of an apple? Can you add meters per second to a push? I mean, of course not, right? It's just nonsense. It doesn't mean anything. And there's actually a formal way to prove that it's nonsense.
This amazing technique is called dimensional analysis. It's basically the process of ignoring all the numbers in an equation and looking only at the fundamental types of quantities involved. Things we call dimensions, like length, mass, and time. Every single thing you can measure can be broken down into these basic ingredients.
Let's see how this works. The dimensions of velocity are pretty simple, right? It's just a length divided by a time. But force? A force is a mass times an acceleration, which makes its dimensions mass times length divided by time squared. If you look at their fundamental makeup, they're just different languages. Trying to add them together is like trying to add apples and kilometers. You just can't do it. They are dimensionally inconsistent. And this leads us to what is basically a golden rule in physics. Checking the dimensions of an equation is an incredibly powerful sanity check. If the dimensions on one side of the equal sign don't match the dimensions on the other side, the equation is guaranteed to be wrong. Period. No exceptions. Now, if the dimensions do match, it doesn't automatically mean the equation is right, but it means it at least has a fighting chance.
So SI units, significant figures, dimensional analysis. You might be thinking, wow, that's a lot of rules. But here's the thing. These aren't just boring regulations to memorize for a test. They are the fundamental grammar of science. They're what allow us to turn a bunch of chaotic observations into a coherent, shareable body of knowledge that everyone can build on. The best way to think about it is as a toolkit. SI units give us clarity, that universal language so we're all on the same page. Significant figures give us precision, an honest way to talk about how well we know what we're talking about. And dimensional analysis gives us consistency, that all-important sanity check to make sure our ideas aren't just total nonsense.
When you put these three tools together, you have the very bedrock of scientific collaboration. This is what allows a team in Europe to build on the work of a team in Asia, because they know, with confidence, that they're all speaking the same language, respecting the same rules of precision, and working with ideas that make logical sense.
It really makes you think, doesn't it? If science has this whole hidden grammar that makes everything work, what other invisible rules are out there quietly shaping the world around us? Think about it. In our languages, in our societies, even in the music we listen to. What are the underlying structures that we just take for granted every single day? It's definitely something to chew on. Thanks for joining me.